see it here in a minute, but you know, if you have a system, if your system is if your system is, your system will tend, let's put it this way, your system will tend to actually disperse energy. It will tend to do this just naturally, just the way the universe works, and your system will tend to become more chaotic. And I'll just put increase entropy. It's just what it does, energy dispersion. And actually, in this lecture, we're going to get to what energy dispersion is. Well, that's an action or process, okay? And then what increased entropy is becoming more disordered. That's what it wants to do just naturally. But we know that there are definitely systems that become ordered, and there are definitely systems that actually are processes that are endothermic, okay? So here we go. And actually, therein lies G, what we call Gibbs free energy, is going to kind of link the two to talk about what we call spontaneity. So what is spontaneity? Spontaneity in general, I'll put an R for reactants and a P for products here, kind of from left to right. Spontaneity means that your reaction is going to proceed from left to right. It's going to proceed from reactants to products if it's spontaneous. Check this out then. Non-spontaneous means that it won't. But in order to get it to go, all we would have to do is go ahead and take my P, go back to my R. So if this is non-spontaneous, if non-spontaneous, then this would be spontaneous. All we got to do is switch the reaction arrow. I just think that's funny. If a reaction is non-spontaneous is written, then all we got to do is reverse the reaction. It becomes spontaneous. Okay. And these are the two things that I tried to say just a minute ago. And these are laws of thermodynamics that a system will tend to want to minimize its energy, disperse its energy, and disperse its matter, increase entropy. So they're actually dispersion of two things, dispersion of energy, dispersion of matter. And we're going to look at some scenarios here, and this is the kind of the non-quantitative thing I want to do today, kind of just eyeballing it qualitatively. This says that if you do have a reaction that's spontaneous, then by golly, you must have something going on behind the scenes. At least one of these two things are going on behind the scenes if your reaction is spontaneous. Okay, so dispersion of energy. I'll go ahead and use the phrase I use. This favors spontaneity. I like the word spontaneity too. Spontaneity. Okay, and this favors spontaneity. Okay, so if it's spontaneous, you must have at least one, if not both, of those things. But hold that thought, because I've got a couple of examples where it's confounded, it's kind of mixed. So here we have sublimation, which is a solid going to a gas. Okay. So you guys would tell me, related to the homework that you're doing, if a solid goes to a gas, that's what? Increasing entropy, right? Yeah.
So entropy is not.
Yep.
I thought entropy was order.
Right. So, no, entropy is a measure of the disorder. Entropy measures order and disorder, but yeah, entropy itself is disorder. Yeah. Yep, you got it. But the caption says that in order for sublimation to occur here, a solid goes to a gas, you need energy is absorbed. I bet you buy that. Energy is absorbed. It's an endothermic, i.e. endothermic process. So what we have is this increase in entropy that favors spontaneity, and actually energy is absorbed. That's the opposite of what I just said here. That's not the dispersion of energy, that's the taking in of energy. So this guy down here disfavors spontaneity. I'll put SP for spontaneity. So, I mean, it's possible. And like I said, we're going to introduce a third variable. When you look at thermodynamic values, they'll have your H's for enthalpy, your S's for entropy. I can come up with slightly different words for those things. And then a G for gives free energy. Gives free energy, so look at the S and the H. So I have another one for you, similar. Just simple sweating, okay? Summer's coming and we'll be outside, humidity's high, and if humidity's high, what's happening here is you have water vapor going from a gas to a liquid. So what do you think? Is that increasing entropy or decreasing entropy? This is decreasing entropy. So very good. So decrease entropy, and it's a decreasing entropy, then actually it disfavors spontaneity, right? Disfavors spontaneity. Well, let's think about a gas going from a liquid, and this is where I tell you this is a phase change. And I'm good about putting energy in. It's harder for me to think about taking energy out. To go from a liquid to a gas, I would put energy in. To go from a gas to a liquid, actually, energy is going to be released. So energy is released, and actually, this energy that in our clouds, I think I might have said this when we were covering this before, but as water vapor condenses to form a cloud, that's a whole heck of a lot of energy. And actually, your clouds become warm, and what we know about warm things is they're buoyant. So actually, in a thunderstorm cloud, that's why it just gets updrafted. So that is what we say, exothermic. Energy is released. So exothermic. Energy is released, and this actually favors spontaneity. So these are two just kind of quick examples of you can have a phenomenon that is kind of conflicted with regard to is this phenomenon that's happening, is it going to be generally disfavored or favored with regard to these two things? Okay. So we need to consider both. The energy change of the system. Is it dispersing energy, exothermic? Is it taking energy in, endothermic? And we have to consider the entropy. Is it becoming more disordered, or is it becoming more ordered? So just so we're all on the same page, I have some slides here to kind of just reiterate what we've been saying. So if delta S, the change in entropy, is positive, that means your entropy is increasing, your disorder is increasing, okay? And that favors spontaneity. I'll put that up here. Favors SP. If you're like me, I still have to concentrate when I think of delta H's. Delta H is negative, that's exothermic. Delta H is positive, that's endothermic. I do have to concentrate. So now we have something else we have to concentrate. So if you have a negative delta S, negative change in the entropy, that means that it's becoming more ordered, and that's going to disfavor spontaneity. Disfavor spontaneity. Not to say that the process won't occur, because it could be carried along by the other element that you have to gauge in order to understand. Okay, we talked about these before. So positive delta H means it is endothermic. And that's the opposite of what Mother Nature wants to do. So this will disfavor spontaneity. And then negative delta H, we said, is exothermic, and that would be the dispersion of energy, and that favors spontaneity. So on your, you might want to be thinking, you guys are good test takers. Your final exam, you can have a sheet of notes, and this Unit 5 stuff already be thinking, well, Unit 5, I might just want to jot that down on my sheet that I'm going to have. Your final exam, just like in Chem 1, you will have some questions over Unit 5. Okay. I've been talking about G, so here it is. Okay, G is called Gibbs free energy, and it is also a state function. It's independent of path. So that's all good. You just need to know the initial and the final conditions. So I have another thing to throw at you. Oh, so you guys know the not things here? Those mean standard conditions. We've been talking about that. Standard conditions are, what, 25 degrees Celsius and 1 bar. So that means 25 degrees Celsius and 1 bar pressure. So this is another thing to get down, and I don't know, I have to concentrate. So Gibbs free energy finally relates to 2 things we've been talking about. It relates your delta H, which would tell whether you're dispersing energy or not. It will relate your delta S, whether you have it ordered or not. Notice we throw in with the delta S, change in entropy, we throw in, we multiply it by the absolute temperature. And notice they have, this is the term with regard to entropy is subtracted. So here's the deal. What if our goal was to get a spontaneous reaction? Our delta G has to be negative. And that kind of makes sense because our delta H, the negative delta H favors spontaneity, right? And a positive delta S favors spontaneity. But the fact that you're subtracting the delta S term means that negative delta G is what we're after. So I guess that's right. Now these 2 slides are similar. In my office, I was like, what? I got that slide twice. But you can see what the difference is. Okay? So any conditions, standard conditions. Okay? But they have the same trend. All right. So let's look at eyeballing some ideas. So if our goal is to get it spontaneous, well, I should just say, I'll come back to that. If delta G is negative, the reaction is going to be spontaneous. If delta G is positive, then the reaction is going to be non-spontaneous. They just have to swing around the reaction to make it spontaneous. If delta G is right at 0, that means that you have, as written, your system is going from left to right and right back to left. It's in dynamic equilibrium. All right. So if you're at equilibrium, this threw me off too. If you're at equilibrium, then delta G is 0. Actually, I think I show it in my next things. And if delta G is 0, then kind of the magnitude of your S, your change in entropy, is equal to the magnitude of your here we go. Delta G is 0, so put a 0 there, rearrange it. Actually, can I show you the derivation of the previous blocks? Then we can go ahead and bring that T over to that side. So this is at equilibrium. But, so I see you guys highlighting some things. So that you guys bring the sheet of notes, and I gave you, this is what I would give you too. So you just need to know how to use it. And I'll go ahead and make mine just like this so you don't have to. I thought, I've never done this before. So would you like to use that as your sheet? Just mark it up.
I mean, like, we can add.
Right, and then the front and back and around. Then you, that seems to be, then you have to rewrite it. Okay, let's do it. Okay, so I wanted to get to this part, and I got a few minutes to think I would get to this part. So we looked at some scenarios where, with regard to one aspect, it was spontaneous, but with regard to the other aspect, it was not spontaneous. So we'll get to that. What if your delta H is negative, that means it's exothermic, and your delta S is positive, that means it's becoming more disordered. And notice that related to your delta S being positive, then this term right here, your negative T delta S, is actually going to be negative. Does that make sense? So in this situation, you can't lose. It's going to be, your delta G's got to be negative. Okay? Totally. If delta G is negative, it's spontaneous. Well, let's mix it up a little bit. Some of the scenarios we looked at with the sublimation or the condensation. Here we have delta H is negative still, exothermic, but now we're going to make delta S negative. Okay? Delta S negative means that it's becoming more ordered. Like, that's going against the grain. So that disfavors spontaneity. So it's not that it won't be spontaneous, or it's not that delta G won't be less than 0 or negative, but if it is spontaneous, we say, what let it get there? Well, it was the term that actually was not fighting the universe. It was, in this case, the enthalpy term that was negative that actually did the trick. We say it'll be enthalpy driven if it is spontaneous, and the only way that's going to be the case is if the absolute value of your enthalpy term is greater than the absolute value of your T delta S term. If it takes over. So I have two more scenarios. Oh, one more thing about this. So, does this make sense? If I want my enthalpy term to take off and my T delta S term to be low, then this actually is more likely the temperature to low. Okay. All right, so here we changed it up. Notice now your enthalpy is positive, which makes it endothermic, which disfavors spontaneity, but we've gone back to your delta S term being positive, which favors spontaneity. So disfavors spontaneity, favors spontaneity. We could go through a similar scenario. It's not impossible for your Gibbs free energy to be negative. Totally, can happen. But in this case, it will be negative only if basically your entropy term took off. So we say that it was spontaneous, but only because the entropy made it happen, so it's entropy driven. And notice that if we want this term over here, the T delta S, to take off, you're better at a higher temperature. Okay. The last scenario is this one. All right, we have, it's endothermic, and it is creating order. Endothermic, energy in, not the dispersion of energy, and creating order, not the dispersion of matter. So in this case, dude, there's no way you're ever going to get it a negative G. That's the fourth of four scenarios. So it will never be spontaneous. So I think that's a good place to stop. I've got a few slides that kind of talk about those four scenarios. And I will go ahead and I'm going to look at, I'll make a sheet in case anybody wants to look at Alta. So you're maxed out at 100%, and for all intents and purposes, yeah, you don't need to turn in any homework. I've just got 100%.
I'd like that done if you can do that for even 5.
For Alta?
Yeah.
So you have options. You have that homework if you want to look at it. And yeah. Okay. Did you like Alta?
Yeah, I think so.
We'll try it again. I'll do that.
Do some homework. However you do it, do some homework. So, very good.